So let's start on the back of your sheet. The back of your sheet has kind of a little table that we've seen before. This has got our reminders about our two different types of particle level pictures. Okay. We're going to make top flap and bottom flap pictures here. We'll get your flaps in place later because we're actually going to make the bottom flap first. So it'll actually be a little easier to do your bottom flap if your top flaps aren't in the way. But just by way of reminder here, our top flap pictures are the pictures from Unit 1 that go with our target reaction 1. It's a very simple particle level picture. We don't show any charges. We don't break anything apart in solution. We, as always, make sure conservation of mass is met. It clearly represents the chemical formulas and the balanced equations. Things that we use top flap pictures for. We use this if we want to demonstrate what it means to balance a chemical equation. So our top flap pictures were our very first version of how to get a chemical equation balanced. You might also use it if you wanted to explain to somebody what a balanced chemical equation was. You could draw them a top flap picture and they would be able to understand what you were doing. It's useful for doing lasso chemistry. As we started to balance chemical equations, we worked on looping things up and saying, well, this is a double batch and this is a triple batch, so kind of batching things out. And if you wanted to go about calculating your masses in terms of AMUs, we did that in our Unit 1 target as well, just like looking at it and counting how many of each atom and how many of each particle and adding up all the parts and pieces. Having everything nice and concise and packed together is kind of useful for that. Our bottom flap picture is a more complex representation of our situation. We're going to include charges on ions and ionic compounds. We're going to break up the ionic compounds and the acids if they're dissolved in aqueous solution. We're going to keep meeting our law of conservation of mass, but this meets our target for matter 3. We did this in Unit 2 when we talked about what things lit the light bulb and what don't. And this is the picture that we're going to need to explain our light bulb observations. So if you have to explain the light bulb, your bottom flap picture is going to help you. Later today, we're also going to be working on movement of electrons, and your bottom flap picture is the one that's going to help you make a decision. Where are the electrons coming to or going from? Or maybe there are no electrons moving. So this is going to help you with the checking for movement of electrons. These are two different representations of the same thing. Think of it as like a globe and a map. Both a globe and a map are representations of the layout of the Earth. In terms of which one you would use, it depends on what you're doing. If you need to take it along in your backpack, I'm going to suggest that map might be more convenient than globe. Globes are kind of an awkward shape. But if you really want to know what's the area of the different land masses in the world, maps create a horrible distortion of the area of different land masses, so it might be better to look at a globe if you wanted to think about something like that. So these are two different representations of the same thing, and we choose the representation that's going to be the most useful for us in terms of what we want to do. Now our goal here is explain our light bulb observations. So we're going to start our comic strip here by looking at our bottom flap pictures, of which I have the first bottom flap already in place for you. I drew the barium hydroxide. You can see all of its ions, beautiful and ready to go. And when we had just the barium hydroxide, we know that the light was on. In order to tell the story, I think it's important that we noticed that a chemical reaction was occurring, and even that we identified that this was likely a double replacement reaction. So let's start by having you and your team write the balanced chemical equation for the double replacement reaction that's occurring. We start with aqueous barium hydroxide. That reacts with aqueous H2SO4. So work as a team and get a balanced chemical equation for that double replacement reaction.
cross, right? Yeah. So.
Oh,
Yeah, there is. It's VAOH, and then it's ES. Oh yeah, sorry. SH2SO2. So then it's gonna be Don't we have to? No, we're supposed to do this first, so that we have to do these two.
Yeah, and then you write it down. So you know how many.
Wait, how? Oh wait, yeah, you're right. So then it's VA. Charge. No, it's us. Oh yeah, you can go. And then what's SO4? It's an acid. So sulfuric acid is 2 minus. So that's yeah.
Then you have to balance it.
Yeah. So what is it?
So you have numbers.
Yeah.
VA is what did you say? 2 minus.
No.
2 plus. And
VA
then
would have to be
SO4 is what? 2 minus.
No.
Okay, they're both right. Yeah. Isn't that balanced?
So that means it's 2 minus is 2
Yeah.
No.
Yeah. Okay.
VA plus
Or is it 2 plus 2 minus?
Oh wait.
and then you draw the
Wait, I.
big place.
I got it.
Look at the card.
Is it VA? Oh, she's doing it. Plus SO4. And then
You get a free AK. And Cordell Patterson. Stats are
You don't have to do it.
No, it's okay. Wait, what did we do wrong?
I did it. I get it.
I don't know.
Do I get it?
So here's our double replacement reaction. I broke down my barium hydroxide into the ions present. I broke down the sulfuric acid into the ions present, did the partner switch. Barium is 2 plus, sulfate is 2 minus. So when I do fill the box on those, they just get together as BaSO4. H is 1 positive, OH is 1 negative. When I do the fill the box, those just get together as HOH. From a balancing standpoint, if I have 2 of these HOHs, I've got the whole thing balanced. Now we need to figure out the identity of the white crud that developed in the beaker. And I think if we rewrite this HOH as something a little bit more familiar to us, we'll be able to identify the white crud. So now let's take this 2HOH and write it as 2H2O. That makes the white stuff a whole lot easier to identify, because we're pretty sure, in fact we're absolutely sure, that that white stuff isn't the water. So that must mean that this stuff is the solid crud that formed down in the bottom of the beaker. Okay, so now we have a chemical reaction. This chemical reaction is going to somehow have to explain what went on with the light bulb. So we've got our first bottom flap picture drawn of our barium hydroxide. Our light is on. And then we start adding sulfuric acid. And at first, the sulfuric acid simply caused the light to dim. So let's start out by adding just a little bit of H2SO4. So let's add just 1 H2SO4 particle. If I think of this chemical equation as a recipe for what's going to happen, if I have 1 barium hydroxide and 1 sulfuric acid, those two things get together to make a barium sulfate, which is going to be a solid. That's the white cloudy junk. And 2 water molecules. Okay, well, let's go with kind of our batching it up idea here. It takes 1 barium hydroxide. So here's enough pieces to make 1 barium hydroxide. And 1 sulfuric acid. So that's my 1 right there. And that's going to create a barium sulfate, which is going to be a solid. So let's put that down at the bottom. So we still have barium ions, but now they're stuck to the sulfate ions because it's not dissolved anymore. And I'll box that in to show that that's the part that turned into the solid. In addition to that, I make 2 water molecules. So here's my products of my first lassoed batch. So if I take the parts and pieces it took to make a barium sulfate, I combine them with the sulfuric acid. Those are the things that I'm going to get. However, I also have some leftover stuff. I need to bring everything else from the beaker here that didn't get used up along to the next beaker. So I still have a couple of hydroxide ions that didn't get used. And a barium ion that didn't get used. And I still have 6 water molecules here that we're doing the dissolving. 6. Plus, the H2SO4 that I added was aqueous. So I'm going to toss a couple more of those in there. Maybe we'll add 3 more for water molecules that came along with the sulfuric acid. And now I want you and your team to talk about why the light got dimmer with the addition of some sulfuric acid. See if you can figure out why that dims the light. All right, so who has an idea in terms of why the light is getting dimmer? Okay, Julia.
Oh, I was the particles, like, they combine in a certain area, which, like, loses the separation that would make it conduct electricity.
Okay, we've lost our separation. Good. The barium used to be free to scoot around and carry a current, but when the sulfate ion came along, the barium ion and the sulfate ion stuck together. Now they're not free to move. They can't conduct electricity anymore. And then the hydroxide ions combined with the incoming hydrogen ions to make water, which is a molecular compound. It doesn't conduct electricity anymore. So even though we added sulfuric acid, which on its own can conduct electricity, the hydrogen ions that could have carried the current actually snagged the hydroxide ions and took away their ability. And the sulfate ion, which could have also helped carry electricity, got stuck together with the barium ion. And so not only could the sulfuric acid not conduct, it started pulling things out that were conducting before and turning them into a form that they couldn't carry a current. We have essentially gone from 6 free ions available to carry a current over here to only having 3 free ions left. And so the light starts to get dimmer and dimmer, even though we're adding something that on its own could conduct electricity. But then we kept going. So let's add another one. Add one more. H2SO4. Well, when we do this, we're still going to have everything we had before. So before we think through what's going to happen, let's bring the other junk along with us. So we still have this barium sulfate that we created in the previous batch. And we still have the water molecules we created in the previous batch, because we didn't dump anything out of the beaker here. So we got all that junk. And now we form a second batch. We still take 1 barium hydroxide and 1 sulfuric acid. So here's the pieces it takes to make a barium hydroxide. And we batch that up with our 1 sulfuric acid that's incoming. And we make a second batch of stuff. So that second batch is another barium sulfate, which I'll stick down here with my first one. So now I have even more solid. I'll box that up on the bottom there. 2 more water molecules. There's my 2 more water molecules. So here's my second batch stuff. So that stuff reacted to make that. And now I don't have anything to move. I don't have any leftovers, but I do need to bring all these water molecules, which is now up to 9. 3, 4, 5, 6, 7, 8, 9. And the sulfuric acid is aqueous, so we'll add a few more. I suppose I should have made these waves kind of going up as we went along to show that the stuff in the beaker is getting deeper and deeper. And in doing that, we can see why the light went off. There's nothing left moving around to carry the electric current. We're down to no free ions. And so our light bulb goes off when we hit what could arguably be called the just right point. I have added exactly enough sulfuric acid to use up exactly the amount of barium hydroxide I have, and I don't have anything left over to carry the electric current. Now, as kind of a side idea here, let's talk about the difference between me drawing these H2Os versus these little ones that just look like V's. When we draw water like that, this is water that's doing the dissolving. It's not actually part of the chemical reaction. The other stuff is just dissolved in it. But this reaction is different in the sense that it actually produces some new water molecules that weren't in existence before. So these water molecules that I've drawn as part of my batching process are water molecules that were produced by the reaction. if I started to try to track the conservation of mass and add up the parts and pieces, or count the atoms, or balance the equation, or any of those things that depend upon being able to find all of my atoms, I need these 4 water molecules because they account for the whereabouts of the 2 hydrogens from the sulfuric acid as well as the 2 hydroxide ions. So I need them in order to account for the complete conservation of mass and the balancing of the chemical equation. Okay. And then lastly, the light came back on again. We stopped briefly and appreciated the light being off, and then I kept adding sulfuric acid. So let's add one more H2SO4. Which means I have everything that was there before. So I need to redraw all this stuff in orange. And the 4 water molecules. But now I bring in some H2SO4. That H2SO4 is an acid. Acids are compounds that produce hydrogen ions in water. So that H2SO4 produces 2 hydrogen ions and a sulfate ion. Which are free to move around, and they bring the light bulb back on again. Because now there's no more barium hydroxide to react with, so the sulfuric acid, which is capable of conducting electricity, can do the job. But we also have 15 water molecules doing the dissolving. And a few more, because the sulfuric acid came dissolved in water. And so we have quite a lot of things here going on inside of our beaker. But I think we've done it. We're back to having 3 free ions. And the more H2SO4 I add, the brighter and brighter and brighter that light is going to get, because at this point, adding more and more and more sulfuric acid is going to serve the purpose of adding more and more and more free ions. So we've managed to invoke the chemical reaction and some of our observations in order to draw a bottom flap story of what went on here. Now let's put the top flaps in place. So take all those things you cut out and tape those in place over the top.
you. Mr. Dorner, mine are like really short and like small. I don't know why.
It's weird.
Yeah. Will I be good?
Yeah.
Okay. Oh wait, why are you? I told you that. You cut them.
I think you cut this part off.
Leia, how do you know it was me? Because I was cutting them.
No, it wasn't me. Never mind. I'm a big
No, I was trying to defend that.
Yeah, why are you so
Acrobat is what? The artist is what you
like,
I ran dirt for a long time. Right now,
I'm gonna be sitting on that for a while, so I'll do the whole work.
Alrighty. Let's fill in our top flap pictures.
he's like at like
Now, if we had to explain this to somebody who hasn't had a lot of chemistry, we might want to go with a simpler version of the story. I think we could still explain to somebody who hadn't had too much chemistry that these two things react to make some white cloudy stuff and some water molecules. And I think if we wanted them to truly see that that's what's going on, this top flap might be easier for them to see. Here's my barium hydroxide, really looking this time like a barium hydroxide. And it's going to make a barium sulfate and a water molecule. And since we're working at the top flap level this time, we're going to eliminate the charges from our story. And that's our white solid. Now we make two water molecules. So here's my first batch of reaction. And so now we have something that really truly looks like that chemical equation. And we could probably even convince our chemistry rookie on the idea of leftovers. We didn't spend this piece, so this piece needs to come along for the ride. It's a leftover. So we have some leftovers. And we have the 6 water molecules we had before that were doing the dissolving, and a few extras that came because we added some sulfuric acid that was aqueous. And then we would point out to our chemistry rookie that we could do this again if we added some more sulfuric acid. Here's another barium hydroxide, which could react with the sulfuric acid that we just added. And we could create a second batch in addition to our first batch. since we now have a double batch, we have 2 barium sulfates and 4 water molecules from our chemical reaction. So there's our double batch, or the second batch is this little collection right there. No more leftovers, except we do need to move all these water molecules and add a few extras. 1, 2, 3, 4, 5, 6, 7, 8, 9, and a few extras. And so that was the just right amount of sulfuric acid. We were able to use it all up. And now that stuff that was conducting electricity is all gone. And so there's no more electricity able to be conducted. And then I can add another H2SO4, but it doesn't have anything to react with this time around. So I still have the double batch that I had already created. There's the ones I already had for those. Here's my 4 water molecules. And my new H2SO4 doesn't have anybody to get together with. So it's just an extra. So there it is, all by itself, because it doesn't have a partner. And we need all these guys. And a couple extra. And so this is a simplified picture of what went on that could be useful if we had to explain this to somebody who hasn't had a lot of chemistry and we didn't want to get into the details about the dissolving and everything else. I think we could still kind of sell this as an explanation. If we know that the barium hydroxide conducts electricity, and that the sulfuric acid conducts electricity, I think we could sell this as it conducts electricity, there's still some of it left, so the light is dimming because there's less of it. Here the light goes off because the thing that we had that was conducting electricity is now all gone. And here, when we add too much, we bring in something else that conducts electricity, and therefore the light comes back on again. So we can make it as a simpler argument as well. What's the best version of the story? Probably some combination of the two. There are probably some of you who understood it very well at the bottom flap level, and others of you who thought, wow, I don't think I really understand that. But maybe now that you've seen a simpler version of it, you can say, that makes a little more sense. But then every step of the way, you can peek under the flap to rationalize 6 free ions. That's going to be a bright light. 3 free ions. That's going to make it more dim. Oh, look, I haven't got any ions left at all that can travel around, so the light is off. And here, I've got 3 free ions, so the light is coming back on again. So it kind of gives you the idea that sometimes these multiple representations are really the best way to create some kind of an explanation to explain your observations and some phenomenon that you've seen. That takes lots of our parts and pieces and starts to put them together. This idea of chemical reactions and predicting the products, and seeing an observation and realizing a chemical reaction has occurred, and being able to think about what kind of chemical reaction occurred, and using our top flap and bottom flap pictures to create an explanation of both the reaction and the light bulb. So that takes lots and lots of things, kind of hooks them together, and hopefully reminds you of where we were before we went on break. Now this is a horribly large, terribly inconvenient sized piece of paper for those of you who have folders and binders. To solve your problem, I want you to fold it over until the holes are just barely showing, and you'll be able to clip it into your binder.